Welcome to the Foundry, an explainer made right here by Forge College. Today, we're unrolling our technical blueprints to figure out exactly how memory efficiency patterns in Sealevel directly impact your runtime overhead. It's a super fascinating topic that really bridges the gap between how you write code and how a blockchain actually executes it. So, let's jump right in.
Okay, so let's set the stage by thinking back to our previous lesson on CPU management. Remember how we learned that compute units act a whole lot like the limited energy of a forklift in a virtual warehouse? Well, Sealevel enforces a really strict per-transaction CPU budget. If your smart contract gets, a little too ambitious and exceeds that budget, execution just halts. Bam! That concrete constraint absolutely shapes how you have to think about your algorithmic costs.
Now let's shift our focus from the forklift itself over to the warehouse floor space, which we call our resident set size, or RSS. This is essentially the portion of memory occupied by a process that's held in main memory. Think of it as our working set. The absolutely crucial connection you need to make here is that every single time we move a box around that warehouse floor, we are secretly burning up that precious forklift compute energy.
So here's our game plan for today. We're going to cover the memory-CPU connection, the naive copy approach, zero copy and borrowing, our diagnostic script, and finally, measuring those trade-offs and costs.
Let's kick things off with Section 1, the memory-CPU connection and the secret costs of memory.
You might not realize this at first, but memory operations actually map directly to CPU work. Yeah, literally. That means totally mundane tasks, like copying data, initializing new buffers, or even just allocator bookkeeping, drain your compute budget just as fast as doing complex math. Basically, every single time you allocate memory, the runtime is slapping you with a hidden compute tax. There's no way around it.
Moving on to Section 2. We're looking at the naive copy approach, or as I playfully like to call it, the digital pack rat.
So this hoarder's approach to coding involves reading raw bytes and then decoding them into brand new objects every single time. You end up creating a ton of transient buffers for every single account you touch. Imagine unpacking a delivery box by putting every individual item into its own brand new, custom-made box before you even look at it. It's crazy, right? It leaves the garbage collector acting like an exhausted janitor, just constantly running around cleaning up your mess.
Which brings us to a much better way in Section 3, zero copy and borrowing, or what we call elegant engineering.
Here is the absolutely crucial takeaway. Maintain the raw buffer and create lightweight views. Instead of moving all those boxes around and repackaging everything like our pack rat, zero copy just looks through a transparent window at where the boxes already sit. You just index right into the buffer without copying the data at all. This elegant technique saves massive amounts of our forklift energy, mainly because you completely sidestep all that heavy heap allocation overhead. It's a real game changer.
And the contrast here is just night and day. Our naive pack rat approach balloons the working set with tons and tons of allocations. But on the flip side, the zero copy method rewards us with a significantly lower peak RSS and a much tighter working set. We are completely avoiding those costly heap allocations.
All right, Section 4, the diagnostic script. It's time for some lab testing.
Now, you might be wondering, why are we using Python here? Well, it gives us an incredibly easy way to isolate these concepts. We can measure these runtime implications directly without actually deploying smart contracts to a network. We just follow these quick mechanical assembly instructions to set up our cross-platform profiling tools. All you need is Python 3.8 or higher, a library called psutil for memory sampling, some mock account data formatted in JSON, and our trusty comparison script. In our script, we're basically setting up a head-to-head battle. In one corner, the naive copy approach repeatedly allocates retained objects by decoding raw bytes into new Python strings. In the other corner, the zero copy view method concatenates raw bytes and simply borrows views into a contiguous buffer using memory slices. The script then actively measures the peak RSS and captures the total allocation so we can see what's really happening under the hood.
Okay, Section 5, measuring trade-offs and costs. Time for the final inspection.
Honestly, the numbers really speak for themselves here. The peak RSS and working set size for zero copy are substantially lower. We're talking 34 megabytes compared to over 85 megabytes for the naive approach. That's huge. And if you notice the time column, avoiding all those allocations actually made the zero copy method slightly faster on the wall clock as well.
Just look at this massive difference in allocation sites.
We have 420 allocations for the naive copy versus just 138 for zero copy. To put that into perspective, fewer heap objects mean the runtime allocator has significantly less bookkeeping to do, which fundamentally lowers our CPU overhead. You're giving the system way less tedious paperwork, allowing it to just focus on actual execution.
Now, a quick reality check. Memory optimizations aren't entirely free. They usually just shift costs around. Consolidating allocations into a single buffer might complicate your code a bit, or add some slight processing work just to manage the offsets. This is exactly why we must measure. You always want to make sure the memory savings actually outweigh the added complexity. As you explore the various courses and learning tracks we offer to sharpen your advanced Solana skills, you'll find that making these measured, data-driven trade-offs is a core theme.
And that brings us to Section 6, Conclusion and Next Steps. Let's look at the key takeaways.
First up, remember that allocations and copies expand your working set and map directly to CPU work. By minimizing full account clones and preferring in-place reads, you can dramatically reduce the number of heap objects the Sealevel runtime has to manage. Second, use ownership and borrowing as practical tools to control your footprint. And third, and I really can't stress this enough, always measure the differences before you blindly go and refactor your production code.
So that leaves us with one final provocative thought. As you sit down to design your next application, ask yourself this crucial question. Will you pay in memory or will you pay in CPU? Because in a constrained runtime like Sealevel, you are always paying one way or the other. Think about how you want to balance those scales as you prep for our next lesson, which is all about balancing resource allocation strategies. Be sure to visit our website at forge.college to learn more about this subject and dive into other great Web3 topics. Thanks for hanging out and learning with me today, and I'll catch you in the next Explainer.